have this cyclic alkene, which would be 1,2-dimethyl cyclohexene. Remember, with alkenes, you start the numbering at one of the carbons of the double bond and then go through the double bond. So this is 1,2-dimethyl cyclohexene. You don't have to say where the double bond is because it's baked into the whole name. If you add hydrogen to this, the syn addition produces a specific stereochemical outcome. So the two methyl groups are on the same side, and the two hydrogens are on the same side of the ring. If that had been an anti-addition, which is the opposite, the hydrogens would be on opposite sides of the ring, and the methyl groups would end up on opposite sides of the ring. And it always does that because of that cookie complex intermediate. You just have a mental picture of that in your head. And it's very exothermic because you're making two very stable carbon-hydrogen bonds. So this is always a very exothermic reaction. It gives off a lot of heat. Then the one below it is a reaction you've had before. This is elimination. In fact, remember when you took the test on alkyl halides, I said everything substitution except KOH, alcohol, and heat. That's elimination. There it is again. So that's not new at all. We've had that before. Now, the bottom, I think there are 3 reactions left on here. Well, there are more. We're not going to cover all of these, but let me just finish up with this this reaction here with a double bond and HX. You notice there are quotes, 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 quotes. That's all reactions of a double bond with 1, 2, 3, 4, 5, 6 different reagents. This is new. This is addition. So for instance, if you look at this reaction, HX adds to the carbon-carbon pi bond. That's not substitution, it's not elimination, it's an addition reaction. The third major class of reactions. Remember, there are only 4. Substitution, elimination, addition, and rearrangement, which we haven't really seen at all yet. It'll actually come up here in one of these mechanisms, but that first one with HX and an alkene is addition. What's going on there? Okay. I'm going to look at this reaction and tie it into everything else. It's not a substitution or elimination, but you can still plug it into the same template because there's a very polar bond, HBr. And you know that that bond breaks readily into H plus and Br minus. Right, so that's like a carbon-halogen bond or a sulfur-chlorine bond. It's a polarized weak bond. Think, is there a nucleophile or a base present? Well, it doesn't seem to be any base present that I can recognize, but there is a nucleophile here that you've never seen before, and it kind of violates the general rule of a nucleophile, which is something with a non-bonded pair of electrons. The only thing that behaves like a nucleophile that doesn't have a non-bonded pair of electrons is a pi bond pair. A pi bond pair is not a non-bonded pair of electrons. But when you consider bond pairs, the weakest bond pair is a pi bond. Remember, pi bonds are weaker than sigma bonds. So, in the presence of an extremely polarized bond, an alkene can actually use the pair of electrons in the pi bond as if it were a non-bonding pair. Now, there's a big price to pay here because you're giving up a pi bond. It's not a non-bonding pair. That pi bond is worth something. But it does work, and the pi bond does essentially nucleophilic substitution so the right-hand carbon of the pi bond ends up bonding to a hydrogen. So picture the pi bond sort of like a mousetrap swinging again. The pi bond swings over and latches on to the H of the HBr, the bromide ion leaves, and you have the left-hand carbon now left holding the bag because the pi bond is gone. So the left-hand carbon is a carbocation. But that's not going to live long because they're eventually going to get together, the bromide ion leaving group and the carbocation. And you're going to end up with HBr added across the carbon-carbon pi bond. First, the H adds to one of the carbons as a proton, leaving the other carbon as a carbocation, and then that eventually quickly reacts with a bromide ion, and you have your addition product. So the first step is really a kind of nucleophilic substitution. The net result is addition, so it's called an addition reaction. And exactly the same thing would work with HCl. The H plus would add to one carbon and the chlorine to the other. Okay? So this is an easy reaction to master. But notice, I'm going to finish up with this, it says Mark's rule. That's short for Makovnikov's rule. Makovnikov passed away many years ago, but his name is still associated with this reaction because he figured out a rule that would predict how this addition would occur in the case where your alkene has two different double bond carbons. So if you're going to add, let's say, HCl to this, the hydrogen could go here and the chlorine there, or now, of course, I'm offsetting the hydrogen and the chlorine artificially, just so you can see that it's the addition of HCl in both cases, but with a different orientation of addition of HX. Where the H goes and where the chlorine goes is different in the two cases. What Makovnikov observed is a pattern. He ran a ton of these with HCl and HBr, and he found there's really no difference there. HCl and HBr add the same way. But no matter what alkene you use, if it's an unsymmetrical alkene, he noticed a pattern that he turned into a rule, because the reality is you don't get a mixture, in this case where two different additions can occur. In most cases you get just one and not the other. So Mark's rule is that in addition of HX to alkenes, the H of the HX goes to the double bond carbon that already has more hydrogens. Some of the newer textbooks call this the rich get richer rule. The carbon that already has more hydrogens gets another one. You're all familiar with that concept. So, looking at this reaction that I wrote here, would the top one or the bottom one be produced? Because the hydrogen, according to Mark's rule, is going to go to the carbon that already has more hydrogens. Now for Monkovnikov, this was just a rule. He had no understanding of why this was occurring. It was very early in organic chemistry. They didn't know a whole lot about reaction mechanisms, etc. They didn't know anything about the existence of carbocations, for instance. But it stood as an important discovery because of its predictive power. So if I wanted to make one chloropropane, this is not a good way to do it. You get essentially none of it. Fine if you want to make two chloropropane. Now, unfortunately, Monkovnikov actually died, actually committed suicide because he was disgraced by other labs who refuted his results. In particular, when you add HBr, some laboratories got the opposite results of Monkovnikov. So he was so distraught over this, and for years was in disgrace as a scientist, that he eventually killed himself. Now, it turned out that the difference is that he was right, but when you're adding HBr, another mechanism, totally different, can take over. That's a free radical mechanism if you have a lot of sunlight exposure in your laboratory. Where Monkovnikov worked was a basement with no outside light. These other laboratories were mainly European labs, which in the old days were converted warehouses with lots of windows for solar heating, basically. And those labs were looking at a free radical reaction that actually gives the opposite to Monkovnikov's rule. But it's a different reaction. So, fortunately, sad case, but he was exonerated eventually. Monkovnikov's rule is correct. And we'll talk more about it. See if you can figure out on your own why it works this way. If you didn't get the reactions, pick them up here. They are on Blackboard, but Andy didn't have scripted. Study these reactions.
Is that for the lab?
Yeah.
Yeah, I couldn't find any, like I went over his recordings and everything. I couldn't